My name is Lorenzo Animali. I'm a PhD student at Roma Tre University in Earth Sciences. And what we are going to go through today is essentially the results of my first year of PhD. And it's about my project, characterization and use of commercial biochar for water purification in real case scenarios. Everything you will see is the result of the combined efforts of my university, Roma Tre University, and Politecnico di Torino. So for our project, we started from three main facts. First of all, that purpose-made biochar has been demonstrated to be an effective pollutant absorbent, so much so that if we input the keywords biochar and water, we can see that research has experienced an exponential rise during the last decade. Second, although commercial biochar is widely available for purchase, it is often, for the sake of soil remediation, it is often not economically competitive with its conventional alternatives. So we are aiming to give it biochar a new high added value application. And third, although as I said at the start, research is abundant in terms of water purification, there is a lack of research when it comes to real study cases. So how biochar behaves for water purification in the real world. Starting from these facts, we set a very simple but challenging objective, which is the one to determine the potential of commercial biochar for water purification in real case studies. How are we planning to do so? How are we doing so? Our approach is essentially two-way. First, a thorough characterization procedure on the material. We need to understand what the characteristics of biochar are in order to determine what are the best conditions for it to be efficient for water purification. While on the other hand, we need to understand what the study case is. Different conditions require different solutions, which must be tailored. So we can relate the characteristic of biochar to its ideal condition to get the most performance out of it. The materials we are using are commercial biochar. So these are biochar that you can go out and buy today. And we acquire them either by talking directly to the producers, or simply by ordering them on their sites. So it's something that it could be a ready solution, and it's something that you can buy today. Obviously, as you can see from the map, we collected 9 biochars from both Italy and Europe, but the focus is on the local context. So most of biochar come from Italy. In terms of characterization, there is a first characterization phase before water treatment, where we aim at determining structural surface and physical chemical properties of the material through this set of analysis. Then, a second characterization phase, which is much more swift, happens after water treatment, as we want to see how biochar changes as a consequence of water treatment. On the side of field studies, we are lucky enough to collaborate with the local authorities, which is in this instance is the Lazio region in Italy, in central Italy, which other than providing us with funding and data, is also a repository of expertise and historical insight on the case studies we are dealing with. So much so, in fact, that this first case study that we will see today was suggested by them. Now we will go through the results that I've obtained in terms of biochar characterization and the water we dealt with. So first, we brought biochar under the scanning electron microscope and collected images at various magnifications to survey what the surface of this biochar looks like. And we also evaluated the porosity that we could find. As you can see here at the bottom of the slide, these are only 3 of the 9 biochar that we employed, but the surface variability is nevertheless high. Then, during this while using the scanning electron microscope, we also perform energy dispersive X-ray spectroscopy to determine the chemicals that are on the surface of this biochar. And as we expected, obviously, they are mostly made of carbon. The main components are carbon and oxygen, and the other elements are only present to small percent amounts. However, it's still worth noting that most samples bear both potassium and calcium, probably due to their feedstock. In terms of crystal phases, once again, it is what we expected. Most of the material is amorphous, as the amorphous fraction is the one connected to carbon, usually. While the most common crystal fraction, which is present across all of the samples, is calcite, while other crystal fractions are only limited, once again, to small percentages. We also measure pH and electric conductivity with a 1 to 10 biochar to water solutions and observe basic pH as is expected across of the samples. We also observe an exponential relationship between pH and electric conductivity. However, pH is not the only factor that influences electric conductivity, as for example, with BC7, with the sample BC7, we see that it could also be influenced by the measured metal contents. In this sample, in fact, the measured metal content is much higher, and so is the conductivity. We have also collected 3 or 4 Raman spectra for each biochar, and they are all very homogeneous, meaning that thermal modifications have little to no feedstock influence. However, in this instance, what we are very interested in is this parameter, the RBS parameters, which is the distance between the D and G peak in the Raman spectra. But why so? Because this parameter can be correlated with vitrinite reflectance and temperature when it comes to kerogen. Kerogen is defined as solid insoluble organic matter compressed and heated by a geological process. So what does it mean? That organic matter gets buried by sediments, and then due to the pressure and geological processes, it gets heated in absence of origin. So if it sounds familiar, it's because it is, and we can consider kerogen essentially as a kind of natural analog for biochar. And in fact, in this graph from Schito et al. 2023, we see with triangles experiments that are essentially artificial pyrolysis on this material. But where does biochar place in these charts? On the left of both graphs, you can see these red dots, which are the RBS values that we register for biochar. Unfortunately, some analyses are still underway, for example, the vitrinite reflectance measurements, and manufacturers are really protective about their processes, so not many of them are not willing to share them with us. However, we've got data for one of the biochars, which is a 550-degree biochar, which has a residence time of 80 minutes. And as you can see from the scale, there is a slight shift with respect to the triangles that you can see in the background. However, this is because these artificial pyrolysis experiments are usually performed with a residence time of 72 hours, while in this instance, this is a little bit more than 1 hour. So biochar formation conditions at the one of kerogens are different. However, if we are able to put the adequate constraints with the relationship between biochar and kerogen, the similarities in the formation process and Raman parameters suggest a comparable behavior. If we manage to find the adequate constraints, we could basically unlock a whole new insight derived from this natural analog, which is commonly employed for the sake of in petroleum industry, actually. Finally, up until now, we performed ion-coupled plasma mass spectroscopy to see the chemical content of the various biochar. In particular, here in this graph, we can see the heavy metal content, as we will see later that we were the kind of elements we were most interested with. And from the graph, we can see that the most abundant element is usually zinc and is closely followed by copper. What we will go through now are the waters that we employed for this first part of the PhD project. And so this means that I must run you through what is our first real study case. That was, as I already said, suggested by us by the Lazio region, which constitutes the local authority in our context. So our first study case is the one of Malagrotta landfilling site, which was once the largest landfilling site in Europe. The landfilling site opened up in 1970 and quickly became Lazio's waste main destinations. Throughout its operational life, it has been subjected to numerous allegations of improper management, and also it has also raised several environmental concerns with and consequently loads of public pressure and closure attempts. After some time, in 2013, the, the landfilling site finally closed down. However, there are still issues related to what concerns site remediation. And these issues are of all kinds. First of all, obviously, environmental, as the presence of a landfilling site has created toxic effects on both fauna and flora, other than polluting the soils with many contaminants, including heavy metals. The due to the land of the across enclosed the landfilling site being degraded, housing prices plummeted with respect to the immediate surroundings, creating a socio-economical gap in with respect to the surrounding areas. Not only the people living close to the landfilling site are less educated and overall poorer, but they have also an higher health risk connected to respiratory, cardiovascular, and tumoral illnesses. Moreover, there are also some loads of pending legal disputes regarding post-mortem management and cost subsidization, as the European legislation, which is currently in place, was not present when the landfilling site was opened, and so there are many disputes still at play. However, this is the sampling map for the area surrounding the Malagrotta landfill. So we chose 4 sampling points, which we thought had the potential for a future on-site experiment. And they are located across a main river, which runs through the landfilling site, between the landfilling site and a petrochemical area, which is still active, and a tributary stream. Through this sampling survey, we aim at creating at assessing the pollutant pathway in the area and frame the chemical analysis that we are performing. And now we will go through each of the sampling site one by one. So in the top of the slide, you can see this graph. The blue columns represent potable water limits. We employed potable water for these evaluations because currently Italian legislation does not provide chemical thresholds for the chemicals we are interested in with respect when using biochar. However, even with potable water threshold, we can only observe a slight breaching when it comes to arsenic in this sampling site, which is next to a petrol station and a farm. Now we move on to the second sampling site, which is along the tributary stream, which in this area essentially becomes a drainage channel that runs between the Malagrotta landfill and an area where there are several mechanical workshops. And in this instance, we cannot observe any breaching of potable water limits. Sorry, it's stuck. Okay. No. Sorry. Okay. Now we've moved down the tributary stream, and once again we can only observe a slight breaching when it comes to arsenic. And finally, this is the last sampling point, which is downstream with respect to the tributary. So after the convergence of the tributary stream into the main channel. In this instance, the breaching with arsenic is significant, I would say, almost double the potable water thresholds, but all the other parameters are still well within limits. So summarizing, heavy metal contaminants are for the most part, so except for arsenic, even below detection limit. And chemical contents do reside even within water thresholds. So on the chemical side, unfortunately for us, the water is actually clean. However, there are a couple of things that I want to point out. First of all, that measured chemical components accumulate along the tributary stream, which is represented by these two bars. So now there could be a source of pollution acting in that area. Second, that arsenic is the only element going above the thresholds for potable water. This, however, is not present. This breaching is not present in the historical records of the last region. So we can imagine that it's just maybe a punctual breaching. And another thing is that nickel is only present in the tributary channel and then gets diluted when it gets to the main one. Now we've got the water from the last sampling point and treated it with biochar, and these are the results. This is the way we set up the experiment. So we ground down 50 grams of biochar to a normal distribution to get the effect of both fine and coarse grain sizes, and immerse them in 1 liter of river water for 1 week. Then we dry the samples and characterize them. What you can see in this slide are periodic tables where I indicated whether there was an increase or a decrease in a certain element. So from this number, we can see that there has been an interaction with water, but unfortunately for us, this cannot be tied to any absorption by biochar, as the heavy metal content in surface water that we can see on the left is 2 orders of magnitude lower than the one that we have in biochar. So there is a fundamental dimensional issue. Moreover, as we saw from the interaction in the periodic table, it could also happen that biochar has leached some of its contaminants in water. Nevertheless, we brought back the samples to the scanning electron microscope, and we observed changes on the surface of biochar. In particular, surface degradation in sample BC1, pore filling in BC2, and foreign matter absorption in BC7. These are all images that are an example for what can happen when treating water with biochar in the way we did. So now, some takeaway messages. So, despite our results, literature still testifies that biochar can be a contaminant absorber, also for heavy metals. We also found out that during the interaction between water and biochar, the structure of biochar changes, possibly getting degraded. If concentration are extremely low, such as in our case, biochar could also leach contaminants in water, and we will investigate further about it. And finally, and most importantly, that the real case studies we are willing to perform require an high contaminant concentration for biochar to express its full potential. So starting from this fact, what will be our future work? We will still continue with our two-way approach. So starting with characterization, we will complete the characterization suite for the biochars we are employing. Then we are moving on to a new case studies of Bussi sul Tirino, which is located in the Abruzzo region, still in central Italy. And now we will be dealing with wastewaters, which will bear a much higher contaminant content, and we'll perform additional experiments in the lab to test whether biochar, especially the dirtiest one, let's say, will leach anything into water. And finally, we are also preparing a review regarding heavy metal absorption from water with pristine biochar, as we believe that using pristine biochar with the right constraints is much more sustainable than both environmentally and economically than going through with a modification. And this is all. Thank you for your attention.
Thank you very much, Lorenzo. That is quite an impressive amount of work for 1 year of your PhD, I have to say. And very unlucky that you live in Italy and have clean water, apparently. I think we have a couple of possible rivers you can check in the UK because the heavy metal pollution is much higher. So if you have any questions, please write them into the chat right now, and we will ask them. I would have a question for the structural changes. You said you had some pyrogasification biochars in your materials. Do they react? Do you see a difference in how they react after water treatment structurally?
No, structurally they behave almost in the same way.
Okay.
It's very similar. The problem usually with pyrogasification is that due to the pyrogasification process, I can tell you that the dirty biochar, the one that we saw with very high contents. Let me go back.
BC7?
Yeah, it's the 7. This is the one for pyrogasifications. And actually, another thing that I can tell is that by looking at it and employing it, it was also we know that the feedstock is mainly lignocellulosic, but it wasn't really well separated. So I also found a lot of foreign matter in here. So we can explain this kind of stuff.
Okay. One question from Gabriel was, have you characterized the biochar after the water treatment with IPC? Maybe there could be some cations and anions exchange between biochar and the water.
Actually, we are planning to do that, but in this instance, we won't go through anymore with the characterization. So this, for example, is part of the post-treatment characterization of the biochar. However, with this study case, we won't go further because biochar hasn't absorbed anything. So given in Italy, the PhD is just 3 years long. So given this duration, we will go through with a more thorough characterization even after treatment, when we will observe that preliminary results for absorption are better than this. Because going through with this, for us, it would mean performing loads of analysis on something that isn't really promising. So now we're moving on to a study case that should be much more beneficial for our sake, obviously. We hope that all waters are clean, but for what we are trying to do, it's a little bit different.
Yeah, it's unlucky to find a river at that location that doesn't have.
And also, we are also a bit angry with the local authorities because they told us that this river could be good, but for us, unfortunately, the waters are too clean.
Christian Wied was asking, why don't you check for PFAS contamination?
We didn't check for that. because what we are working with right now and what is our main expertise here at the department is mostly with heavy metals. So we are concentrating right now on heavy metals, and also because we wanna give like on these biochar studies. I didn't say that, but um, half of the team actually we are all geologists, so we wanna give a different vision on how to design this kind of studies and how to get to know materials and use them to their full extent, also relating them to the study case. So we are choosing a very specific set of pollutants, and then working with that and working with what we are more familiar with, because obviously all these metals of this kind of chemicals are very common also in earth minerals. So as we are doing with kerogen, we are trying to motivate lots of our knowledge into this new field, as we are projecting into material science as geologists.
Yeah, it's very interesting how the geology, petrochemical geology side is coming into biochar research recently. So it's also very interesting what you talked about the kerogen artificial pyrolysis, which I like the word artificial pyrolysis. Um, so
Yeah, essentially that is a geological process that in nature it happens. It happens through tens of thousands or even millions of years. So for us geologists, let's say 72 hours is very artificial, because nothing in geology happens that fast in sediments.
yeah, no, I like the labeling. That's it. So yeah, thank you very much, Lorenzo. You still have a minute or so to write your question into the chat. I will use the time to also advertise our next webinar in 2 weeks. I think it's the 14th of December. We will have Sean Thomas from the University of Toronto talking about biochar seed coatings for precision aerial seeding. And then a second presentation from Marshall Mermel about adoption and commercialization of biochar. So if you're interested, join us just before Christmas, almost. Um, and you had one question from Vahid. So the last question for today. What is the size of pores? Can you specify
Oh, right.
maybe?
Am I sharing? Yes. I will go back to that slide. Yeah. I don't know if you was referring about this.
Mhm.
So here, for example, I don't know if you can read well in the slide, but in BC1 we got pores that are like in the order of tens of nanometers. So here is 40 nanometers, 35, 45. While in BC3, in the zoomed image, we are like in the range of 15 micrometers, something like that.
Okay, great. Yeah, I think that was the question. I'm not 100% sure, but yeah. Otherwise, just write a follow-up email.